effect of nucleophile. SN2 mechanism involves only one step, and it involves a nucleophile. That is a rate determining step of SN2 mechanism involves a nucleophile. Hence, stronger the nucleophile, faster will be SN2 reaction. Faster will be the SN2 reaction, or higher will be the rate. Higher will be the rate of SN2 reaction. Nucleophile is a species capable of donating a pair of electrons to carbon atom in organic reactions. The atom that donates electron pair to carbon atom is called donor atom. For example, oxygen atom is a donor atom. In the nucleophile, hydroxide ion. The ability of a nucleophile to donate electron pair to carbon atom is called nucleophilicity or nucleophilic strength. It is an ability, and hence it can only be compared among a set of nucleophile. That is, it do not have an absolute value. Based on the nature of a donor atom, there are three generalizations about nucleophilic strength. They are, first one, if the donor atom is identical. Donor atom is identical. Nucleophilic strength. Nucleophilic strength increases with increase in electron density around the donor atom. As an example, hydroxide ion is a stronger nucleophile than water. In water, oxygen atom have a delta negative only. Both OH bonds are polar, and hence oxygen atom have a slight negative charge. In hydroxide ion, oxygen have a unit negative charge. Alkoxide ions are even stronger nucleophile than hydroxide ion. It is due to plus I effect of alkyl group. It increases electron density around oxygen atom. In all these three examples, oxygen atom is a donor atom. So, as an intensity of negative charge or intensity of electrons around a donor atom increases, nucleophilic strength also increases. Similarly, carboxylate anion is a weaker nucleophile than phenoxide ion. Carboxylate ion have two energetically equivalent resonating structures. So, negative charge is equally distributed between two oxygen atoms, and hence intensity of negative charge will be lower than that in a phenoxide ion. In phenoxide ion, negative charge is localized to carbon atoms in the benzene ring. Since carbon is less electronegative than oxygen, this type of resonating structures have less contribution to resonance hybrid. That is, intensity of negative charge is more on oxygen atom of phenoxide ion than oxygen atom of carboxylate. Phenoxide ion is a weaker nucleophile than hydroxide ion. In hydroxide ion, negative charge is not at all delocalized to any other atom. So among carboxylate, phenoxide and hydroxide, nucleophilic strength increases from left to right. Another example, RCH2O-. It is an alkoxide ion of a primary alcohol. R2CHO-, alkoxide ion of a secondary alcohol. And R3CO-, it is an alkoxide ion of a tertiary alcohol. Here also, when we move from left to right, intensity of a negative charge on an oxygen atom increases. Consequently, nucleophilic strength increases from left to right. It is due to plus I effect of alkyl groups. Here is only one alkyl group. Here there are two alkyl groups. Here there are three alkyl groups to show plus I effect. As a result of cumulative plus I effect, the intensity of negative charge on oxygen atom increases. That is, among alkoxide ions, nucleophilic strength follows. Primary lower than secondary, lower than tertiary. Then second one, if donor atoms belongs to the same period in the periodic table, nucleophilic strength decreases from left to right across the period. For example, CH3 minus NH2 minus OH minus and F minus. First one, methanide ion or methyl carbanion. Second, amide ion. Third, hydroxide ion. Fourth, fluoride ion. Here the donor atom is a carbon. Here nitrogen. Here oxygen, fluorine. Atomic number of carbon is 6. That of nitrogen 7. Oxygen 8. 9 fluorine. So when we move from left to right, nucleophilic strength decreases. Fluoride is the weakest nucleophile in this group. It is mainly due to increase in the nuclear charge. Here the nucleus of carbon contain only 6 protons, here 7, here 8, here 9. As the number of protons in the nucleus increases, the valence electrons are more tightly held by the nucleus. Hence, release or donation of electron pair become difficult. decrease in the nucleophilic strength is mainly due to increase in the nuclear charge. As nuclear charge increases, the valence electrons are more firmly held by the nucleus. Hence, the lone pair electrons become difficult to donate. Now last, if donor atoms in the nucleophile belongs to same group in the periodic table, nucleophilic strength increases down a group. It is mainly due to increase in atomic radius. As the size of atom increases, valence electrons are less firmly attracted by the nucleus. Hence, lone pair electrons in the valence shell will be readily available for donating to carbon atom. In other words, nucleophilic strength increases. As an example, among halide ions, iodide ion is strongest nucleophile, followed by bromide, followed by chloride, and fluoride is weakest nucleophile. Iodide ion is largest in size, hence these valence electrons are less firmly held by the nucleus. Therefore, lone pair electron can be easily donated. Similarly, among hydroxide ion and hydrosulfide ion, hydrosulfide ion is a stronger nucleophile. Another example, among phenoxide ion and phenosulfide ion, the second one is a stronger nucleophile than first. Here the donor atom is oxygen, here the donor atom is sulfur. Sulfur lies below oxygen in the periodic table. So these are the three generalization about nucleophilic strength. So once again repeating, nucleophile is involved in the rate determining step of SN2 mechanism. Therefore, as nucleophilic strength increases, rate of SN2 reaction increases. Nucleophilic strength or nucleophilicity is defined as the ability of a nucleophile to donate electron pair to carbon atom.